slides, people are still coming.
Okay.
This was an announcement for sitting only.
Okay.
I need to make sure that the second talk starts at what time?
Second talk should start half an hour before the very end. So that means...
It's 12:30.
So it should be in 45 minutes.
Yeah, 45, 12:30. Yeah. Okay, so that's what we need to guarantee.
Maybe we should leave the door open for the air.
Okay. Okay, we are already at 47, so it's better if we start. So welcome to this second session of the morning. So we will start with Manuel. He will tell us about QFT as a set of coupled ODEs.
So thanks, Joao, and thanks to the organizers for the opportunity, especially for the opportunity to use slides, which is very nice, and I will try to reward you with some nice pictures. So the question, or a question that should be in the back of all of our minds, especially if we care about the Bootstrap, is also whether there is a way to define local correlation functions in QFT with a similar degree of sharpness that we do in CFT. And what we argue is that it seems like it might work if we think of the QFT as living in ADS, okay? And with the viewpoint that, of course, at the end, what we want to do is to take a flat space limit and eventually extract the S matrix in flat space if the flat space limit exists, and it's not the kind of limit like with the IKKT as was shown by Joao yesterday. But so the viewpoint that we want is we want to eventually construct QFT in flat space, be able to compute the S matrix, and the viewpoint we take is that QFT in ADS is a good starting point. And this work, what I will present today, sits in the elephant, the space that is the space of approaches to computing correlators in ADS. So we have conformal bootstrap from the boundary, we have Hamiltonian truncation, we have perturbation theory, and what I will show is another method to compute correlation functions in this setting that will be fully non-perturbative. And okay, so the order of the slides, these two was reversed, but yes, we want to get to flat space eventually. So what is the main idea? The main idea is to consider, for simplicity, we focus on 2 dimensions so that we don't have to think about spin. And the main idea is to consider some God-given action of QFT in ADS deformed by some relevant operator.
There was a pointer.
Yes, I have it. And
Sorry, I have a question, but what is QFT in ADS?
so, okay, if you want, what I mean by this is like some free theory or a CFT, a boundary CFT, okay? That's what I mean. Something for which you have all the data in principle, or it's computable. And then there is such a thing as a set of QFT data when you do QFT in ADS, meaning that if you know the scaling dimensions of all the boundary operators, their OPE coefficients, and the coefficients that appear in the expansion to the boundary of the bulk operators, then you can reconstruct all local observables with some caveats in the meaning of regions of convergence, etc. But this is a complete set of data which now are functions of this parameter lambda, okay? So in particular, they will flow, they will change as you go through the RG flow. And what we do is we take some infinitesimal change in this parameter, and we do one step of perturbation theory, but we don't assume that lambda starts as small, just this delta lambda will be small. And with this, we can compute the first derivative of all of this data in terms of the data itself by basically doing perturbation theory with conformal blocks. So in the end, it will all be model independent. And what we will get is some system of ODEs that relates all of this data at any point in the RG flow. And the statement is that if you truncate this system, it seems that there's good ways to truncate it. The sums that you get converge quite fast. and so this the system can be iteratively solved.
So for this, you need to kind of assume that you have this for various lambdas, and my question is, like, what do you mean by phi hat as lambda changes? For instance, I can understand that maybe in free theory, but sorry, in flat space, but in ADS you also have like ADS radius. So won't that let phi hat to like mix with any basically other operator, because you can have powers of R?
Yeah, so here I'm assuming a setting which I have only one relevant operator in the bulk. But yeah, that's a good question. Okay.
If I had also dependent lambda, we just take the theory and we turn on a small lambda, and then we get a new theory with a slightly different phi hat, and then we just keep going. You can write an ODE, then this answers Peter's question.
I guess, yeah, I guess this is basically, these B's are the identikit of what is this phi hat, okay? Essentially, all of the information of what is phi hat is in its coefficients to the boundary, because it's like the form factors or everything you want to know about it.
I'm supposed to.
I suggest that you let Manuel just go a bit further explaining what these variables are, because of course you already know, but more than half of the audience probably doesn't really solve the definition more carefully. And then, because these are all very conceptual and important questions, but maybe we can wait a little bit so that the talk starts.
You are the advisor, so let us handle now.
I'm not worried about Manuel. I'm worrying about half the audience that still did not understand the idea, because
Oh, everybody understood that.
Okay, I will get to some plots, and I think the plots cannot be argued against, and then we can try to understand together, because I am confused as well on
Maybe let me reformulate very quickly.
Yes.
Sorry. So, say when we have, if you were perturbing in flat space by a relevant operator, then usually there is like no ambiguity, because you cannot like redefine lambda essentially by, you can say that, oh, what I mean by lambda is actually like lambda plus lambda squared, because this doesn't pass like the dimensional analysis, roughly speaking. But now we have the ADS curvature. In principle, I can redefine lambda to be any function of lambda and the ADS curvature. Yeah, so I'm just.
yeah, there's some ambiguity in lambda, there's some ambiguities even in the B's. My point of view is that you can make a choice, and you can be consistent with the choice. At least in the cases we checked, the answers make sense with the choice that you make. And then I agree that there's a lot more to think about, for sure. It's not super clear to me.
All right.
I agree that there's okay, so I have to mention that the inspiration for this work was mainly from this paper by Connor, where he did it for 1D conformal manifolds, meaning some CFT in 1D deformed by a marginal deformation, and then you can get similar ODEs for the first two, and so that's what we started from. And then some paper by Hollands and Wald, where they were trying to do it in flat space, but it was a system of equation that was intractable in the end. Okay, so first of all, let me explain what I mean by that QFT data is everything for these observables. So I'll first just set up the notation. I will use embedding space because everything is simpler. X will be points in ADS, and P will be the boundary, so the light rays. And the Poincare metric will be with this notation. And so the point is that at any point, for any value of this lambda, the two-point functions on the boundary will have this form. They will only depend on this function that is the scaling dimension of the operator. The three-point functions will have this form, where the OPEs are the new set of data with respect to this. And the bulk to boundary two-point function will have this form, where here the B coefficients will appear. And these B coefficients are also, as I was saying, what appears in the decomposition to the boundary, or the form factors of these operators with the vacuum. Okay, so what we do, and so any other correlation functions, for example, you take a three-point function in the bulk, you can expand all three operators to the boundary, and then you get the OP coefficient on the boundary, and you will get some conformal block here. So in principle, every correlation function can be decomposed in this way. In particular, if we only care about boundary observables, then you don't need all the bulk operators from the QFT, you only need the operator that is deforming the theory, or if you want, the trace of the stress tensor. And then to derive these ODEs, as I was saying, we solve perturbation theory, and we do that once and for all in the sense that we do this infinitesimal change using the conformal blocks, and then you will never need to do these perturbation theory integrals again, because you just did it one step universally, and you just iterate these differential equations.
So what's the difference between the first two sets of observables?
That here, this is the full set of bulk operators, and here I'm restricting, I'm saying the only thing you need is the deforming operator. Okay, so how does this perturbation theory work? Basically, as I was saying, you change infinitesimally the coupling, and at leading order, the only effect is that you will get these derivatives for the data. And
sorry,
yeah.
question. The index ijk in the first two equations, is that the same I as in the last equation, or should that be a different letter?
This is the set of boundary operators that appears in the expansion of this bulk operator to the boundary.
But the labeling of the bulk operator is not the same as the labeling.
No, I agree. This I, in fact, is not for the bulk operator. It's O hat into OI on the boundary. Maybe it's
Hats for bulk, no hats for boundary.
it's not a great notation.
That's
Maybe,
what I'm confused about, because I would say that if I put a hat on the operator, the index should not be an I, should be a
Yeah.
different letter.
so this is not the index. In fact, this is not the subscript of O hat. It's another subscript.
O hat OI.
Yes, it's O hat OI.
There's a space.
Yeah. Is it a pen? I meant, yes, B,
Just draw it on the screen. It's fine.
O hat, OI.
So
Okay.
it's a symbol of hat,
Yes.
this picture, and then that's
Yeah, sorry. Okay. So you can compute the two-point function for the bare operator in the next, as you shift this delta lambda, and by pulling down the action, you will get some three-point function with the insertion of the bulk operator now. Then you need to integrate over. And the idea is that you need to regulate, of course, this will diverge. And we regulate using these epsilons, these little circles around the boundary insertions. And so you will define some renormalized operators, and they will, we impose at this point that they don't mix, they are diagonal, and their two-point function will be with this shift in the scaling dimension. Okay. Now, how to do actually this integral? You need to, First, yes, there's what will happen with the other equations is you will have higher point functions. For the OP coefficients, you need to do a 4-point function where you have one bulk operator and 3 boundaries, and the bulk to boundary coefficient will be one bulk operator, one at the boundary, and other bulk operator integrated. And here you don't need to regulate around this, because in 2 dimensions, when they coincide, the divergence is integrable. And okay, so to do that universally, you decompose into conformal.
Assuming that it's a relevant operator.
Yes, exactly. You do this. You basically introduce the resolution of the identity if you want. You can think of it that way. Then this is the 3-point function. It's where C will appear, and this is the bulk to boundary coefficient, and the rest is a conformal block, which depends only on some conformal invariant combination of the 3 points. And now comes the greatest technical difficulty, which is that this sum and this integral cannot be swapped when you use usual conformal blocks. So this is the big technical parenthesis that I will not go into large details on, but the resolution is that you need to use local blocks, which is basically an alternative basis where each block is not a representation of the conformal group, but it's some linear transform. So if you take an original block, you act with a functional, you get a local block, which has the property that the sum over these blocks converges to the same correlation function when you take when you put OP coefficients in front. but moreover, it has the right analytic structure, meaning that as opposed to the normal blocks, it only has a cut when the operators are inside each other's light cones, while the original blocks have also, if you just naively compute them, they also have an unphysical cut. And that makes this sum and integral non-swappable. So we needed to do this. And there is, importantly, they have some extra free parameter. And what happens to be the case, we showed that basically if you act with linear functional on the integral of the block, it becomes the integral of the integrated block, which is, of course, is not obvious, but we checked in the sense that we did it both ways for the first two cases, and the answer matched. It's no, you can really write it as a functional, that you take the block and it's a Mellin integral of the block against some kernel. And okay.
I was just saying that when you take a function and apply a linear function, we get a number, not another function.
Oh, sorry. Yes, of course. Yeah. Fair. Yeah, it's sum up. Yeah, from a function to a function. Okay, so what do you get when you do this? For the first equation, you get, okay, what I was showing before. You will get the expansion to the boundary of the deforming operator, then the OP coefficient of these guys, J, with your the operator you're flowing, and this integral, which in this case happens to depend only on delta J and not on delta I. Then for the bulk to boundary case, you will get the expansion of the bulk guy that you're flowing. Okay, this should be phi hat. The expansion of the deforming operator, their OP coefficients with, so J, K, I, and the integral of this object. And for the 3-point function case, here there's a subtlety which you will not be able to use. You know, you want to use blocks, then you have to go to different channels in different regions for the integral, for the composition to converge and for you to do the integral. And so you get ST and U channels, and you will get the expansion to the boundary of the deforming operator, and then the various combinations of OP coefficients. And this was the thing that took us basically 1 year.
What's the role of alpha?
Alpha is an arbitrary parameter that you can choose. If you send alpha to infinity, you go back to the normal blocks. But there is basically an ambiguity where here really you can choose any alpha you want. Here it turns out that for these sums to converge, you have to choose alpha such that it grows with, now I'm confused, okay, one of the two labels, meaning, okay, there's a special ordering here, but now I cannot remember now.
So I'm confused. So the differential equation themselves depend on alpha?
Only if you truncate. So, okay, this is another thing. If you sum everything up to infinity, the dependence on alpha cancels out. Since you don't do that, and the whole point is, this whole problem of having to use local block is because you want to truncate the sums. And if you truncate the sum and the block has the wrong analytic structure, you will never match the correlator. So, I mean, you can match it in some regions, but if you want to do the integral and you want to do this swapping, then yeah. With the truncation, you need to use these local blocks. Okay.
Alpha only depends on delta I, not on delta J.
No, unfortunately here you have to grow alpha with one of the sums, but that's fine. Because
I thought you have to first fix alpha and then derive the equation.
no, because basically this transform here, you do it, this transform is with respect to one of the scaling dimensions in the block. And you want to do it with respect to the scaling dimension that corresponds to the boundary operators of the deforming operator. Then you cure that sum, because that's the sum that doesn't, that is problematic. The other sum is independent, so you can see it as you carry out that sum to a high truncation with this alpha. Then you forget about alpha, you get some number, and now you carry out the second sum.
And maybe you shouldn't write alpha, you should write alpha J or alpha K.
Yeah. Yes. So here alpha should be alpha J or alpha K. Yeah. And here it should depend on, it should grow with S. for example, with delta S. Okay. So let me get to the concrete examples and checks so we can agree or disagree. So let's consider GFF in ADS. So we have some, here our big phi hat is phi squared, and the coupling is the mass squared in units of the radius. And okay, so you have, for example, primary is phi and phi squared n, all the double traces. You have some relation between delta and the coupling, also for the double traces. It will just be this. And so, and moreover, you have these B coefficients, you compute them basically by taking the two-point function and expanding it at the boundary. And you see that phi has this is just such that the two-point function of the boundary operator is unit normalized. You do it for the double traces, it's some complicated ratio of Pochhammer symbols. And then you take derivatives and you check whether these infinite sums of blocks, integrated blocks, actually converges to the right number. So for the scaling dimension of the boundary phi, this derivative is just this. And on the right-hand side, you have this sum. And okay, as I said, this you can compute from this. The OP coefficients, you can compute them from harmonic analysis, for example. And here, just to be explicit, this integral, in the simplest case, is just a ratio of gamma functions. So it's very tractable. And it knows about, you can already see something interesting, which is that it knows about marginality. Basically, when the boundary, when one of these operators hits marginality at the boundary, then if you integrate this equation, you get a square root type behavior, which is what you expect, and the splitting and the merging. And so you can run this with some truncation, and you can see, for example, here with the blue dots, I'm using just the normal blocks. The truncation is just 5, so I'm summing just 5 operators, and the blue dots fail to converge after this particular value of delta phi. It should be delta phi. And the local blocks keep working well. How well? We have to check the relative error. And you can see that you can go to arbitrary precision, basically. This is n max now, the truncation. And these are different choices of alpha. So the role of alpha is that if your computer, you can only take 5 operators, then you should probably take a low alpha. You get a 10 to the minus 3 precision already. But if you really want to push, then you can take a large alpha, but then at the beginning you're really getting something bad, and only later on you get something really, really good. So this is, you can play with alpha in this way.
But this is because you already know the answer. What
Yes.
If you didn't know the answer? How would you choose alpha?
So you know, so there is this estimate that you can make of the error. So the error for some delta max will be you can estimate it to be with this power, where again you have to think that there is this problem at the beginning. So you might think by looking at this, okay, I should just take alpha to infinity, but for any fixed alpha, if you take alpha to infinity, you get back to the normal blocks. So you don't want that, meaning that this curve essentially will start going up and you will never reach good precision. So you have to play in this way. Alpha in the order of n max.
For n max 5, who is the best one? N max 10, orange is the best one. 15 green is the best one.
Sounds good. Yeah, maybe. I don't know. Yeah. We have to make. We didn't fully study the full efficiency. For now, it's like proof of concept. Yeah, but I agree.
Sorry, Manuel, how did you estimate the error?
It's just because we know the answer from before. This estimate.
Yeah,
Basically, you have universal behavior for large delta for these B coefficients and for the OP coefficients. And this is some function that you have. And so you can check you fix some large truncation and you do the integral of the tail. And that's the answer. Okay. And so you can try with the bulk operator expansion with these B coefficients. And now it starts to become more complicated. You have 2 sums. The OP coefficients also start to be more complicated. And the integral is much more complicated. Now it's a 3 of 2. but it's still some analytic function. And again, it has this property of the thing at marginality, and you can check that it again works. Now I'm summing 10 operators, or well, 10 times 10. And if you look at the errors, the situation is worse. You can get to 10 to the minus 3 if you sum up to 30 operators. But this is, again, we didn't study fully what is the optimal choice. So as I said, here you have to have alpha growing with P, which is this label, for example. And we saw that by choosing this, the errors were decreasing. If it doesn't grow fast enough, then you don't decrease the error. So this is a whole study that needs to be done systematically, but we haven't yet. And the last check is for the OPE coefficients. And now the situation is, so here we're looking at some trivial OPE coefficient, okay? It's like phi identity, which is just 1 if your two-point function is normalized, and its derivative should be 0. This is the simplest check you can do. And now the situation is a bit more dire because these integrals, we now have them only as some triple Mellin integral, which numerically converges, okay? But to do a check of this equation on a laptop, it runs for 40 minutes. So it's not great. But I mean, maybe it's definitely possible that someone manages to write this Mellin integral carrying it out, I don't know, find some analytic function. So that you don't have to numerically integrate every time. And the errors are okay also here. But here the error, what do I mean by the error? I'm just looking at the absolute value because I'm comparing to 0. So, but it's just going, you can see that it goes to small numbers fast. And okay. So
the Mexico safe is so much better.
Sorry?
Why is
Ah. Probably numerical errors, yeah, because here, so this is a sum, sorry?
Does it cross 0 or something?
No. It could be that it's oscillating. Here I took the absolute value. I don't remember. But so imagine that each of these i's, you need to run essentially, it's a linear combination of Mellin integrals. So it's like 9 Mellin integrals, then you need to sum. It's numerically, there can be errors everywhere, and I didn't do it in a very careful way. Meaning like trying to make it super efficient. I didn't. So, okay, so this was the checks. Of course, the first thing you want to do is to then check interacting flows. But for now, it seems that this idea works. And once you have these differential equations, there are no divergences to deal with. It's non-perturbative. We don't assume unitarity and locality, actually. And there are some non-trivial checks also for fermion GFF. So,
sorry, which interval you're not assuming locality?
Meaning that you could imagine having, for example, we're not assuming the presence of the stress tensor in the bulk, and you could imagine also having an action in the bulk where you have bilocal interactions. You don't break, as long as you don't break AES isometries, we're not assuming that the action in the bulk is local.
But the deformation is local.
Yes.
The integral of a single local parameter.
Yes, 1 second.
The theory of perturbance would be boundary CFT of some.
Yeah.
Go to ADS or switch this ADS to boundary.
Yeah, once we have the differential equations, you get, yeah. For example, one case that we would like to try is long-range easing, where you can see as GFF, and then at some point you turn on O to the 4th on the boundary, and you keep using these equations to continue the flow. So in that sense, it's non-local in the sense that you have an interaction that is only.
Certainly not local, but the bulk, I'm thinking about the word. I thought locality.
Yes.
I think the bulk theory can be non-local as long as. So your initial condition for these ODEs can describe a bulk theory that's non-local. Okay. Yeah, I think it's fine if you use initial conditions for these ODEs that define a QFT and ADS that's non-local.
you just have to evolve away from that initial condition using a deforming operator that's local.
Yeah, I don't remember.
Well, I mean,
what I had in
if
mind.
the theory is non-local, you can ask what is a local operator. So I think for that it's important what Slava said, that you can think about this as being a boundary maybe for another ADS, and then, yeah, that makes sense.
Okay. Yeah, I don't stand by that statement. I don't remember what I meant. So short-term wishes that we have is to improve efficiency of these equations, the way we're implementing them, and then to try to solve some simple interacting cases. For example, this long-range easing or the Lee-Yang flow, where you have one relevant deformation. That's the thing, because then if we have more to do easing field theory, you need to generalize. And then there is this idea, yes, indeed, can we phrase these differential equations without talking about the coupling at all? So like relating to the lightest dimension, everything else, and is there a way to get rid of these B's? There's some sense in which they are redundant because they solve an infinite set of constraints coming from this locality. Meaning in the papers by Miguel and Nat, they show that there's an infinite set of sum rules that these B's satisfy. So maybe there's some way that you can rearrange all of these without even talking about these B's. Or maybe you have to talk only of one of them. And yeah, so we would like to generalize to multiple deformations, of course doing easing field theory, on a linear sigma model, and then if we dream, then we want to do higher dimensions, and eventually it would be amazing if you could use this method to attack phenomenologically interesting questions. And so just to close, I wanted to say that also, if you care about axiomatic QFT, then you can think that this might be something interesting because it inherits all the axiom of CST except for the boundary stress tensor. Then you supplement it with these equations and with the B's, and then everything is sort of concise and well defined. And so talking about locality from before, if you have a bulk stress tensor, then there are some extra sum rules that these data satisfy. So are these following from the equations we have, or are they something you need to add? It seems to be that they don't follow, right? Something extra. So that's it. Thanks.
More questions?
So if it's safe to go back to philosophy now, I think everything all the checks you showed were for boundary observables, which is why you only needed the B for, B phi hat I,
Yes.
right? So the boundary observables encode the S matrix, which is a field redefinition invariant object. So that might be what makes Peter's concern resolved in this case. I don't know either, of course, so it would be great to get thoughts.
I've resolved my concerns.
Great.
Sorry, my question was actually similar. So the boundary observables are related to the flat space S matrix. Is it conceivable that that you could take the flat space limit and have a flow equation directly for the S matrix?
So, I mean, from what I understand, it's like you keep flowing these observables, and eventually you can see it as this coupling is in the units of the radius. So you can see it as the mass scale is fixed, and you're going towards flat space. So as you should look at the asymptotics of these equations as you keep iteratively solving them, and that's what tells you the observables in flat space. But I wouldn't know how to. Yeah, I don't. At least I wouldn't know how to do that. Yeah, I don't know if.
Yes, so flat space is at infinity. So couplings in flat space would be ratios of two couplings if you have here.
I'm curious to hear what do you mean that you resolved your confusion. Maybe you can resolve mine too. Okay, we shall.
More questions? Can you pass
So yeah, just want to understand a bit the logic behind this. So, what kind of theories do you expect that this approach could let you access? Meaning, you're starting from a from a free theory, from a CFT. So this flow clearly will let you explore a neighborhood of this theory. But say you want to study some strongly coupled theory, which is defined in terms of some, deformation of weakly coupled one. Do you think this approach can still work? Or?
Yeah, this doesn't have to be a deformation of a weakly coupled theory, meaning that the thing I start with can be data from a boundary CFT that is strongly coupled, maybe it doesn't even have a Lagrangian description. And then you deform that with a relevant deformation. You don't need a Lagrangian description even. So
but maybe the question is like, say you want to study, I don't know, young males. So you define it as weak coupling, then it's strongly coupled. Do you think the flow equation will still converge? Or do you think?
So there's nothing in the flow equations that tell you that they shouldn't converge. Of course, until you do it, you should be careful. But a priori, there's nothing special about free theory or weakly coupled theories in this framework.
Yeah, I'm more concerned with the risk of convergence, rather than the fact that you're starting from a free theory.
But
okay, maybe we'll talk later.
so at no point I assume that this lambda was small, right? So in principle, this is you have some derivatives at some point of some functions, and then you keep adding these derivatives infinitesimally, and you continue. It's not a sum that has to converge. So there's these sums, okay, but they have nothing to do with usual perturbation theory sums or whatever.
But what will you see if this line of theories terminates?
If these lines of theories terminates.
So I think indeed, maybe a better way to see results.
So the mic is for YouTube.
Well, I would like to be recorded.
It's off now.
So
I think
better
it's
way
off.
to see your results is that for... is it also camera or not? Am I supposed to look at it?
No.
To smile? So the better way to think of your results maybe is that for any theory you can, which satisfies certain axioms, you can define infinitesimal deformation, well, actually more than infinitesimal, like finite distance deformation, and then you can keep going. But then, some deformations may disappear. In fact, for ADS in QCD and ADS, for certain boundary conditions, that line of theories is expected to disappear. And so what is going to happen?
So
We also talked about square roots. Maybe this is
Yeah,
related.
yeah.
So what are you going to see if things disappear?
So I guess, for example, in the case of ADS, this Dirichlet that is thought to be annihilating with this star, what you would see is indeed there's a square root there, but if you go to the plot of this scaling dimension with respect to any other, these lines are always continuous, right? It's just that, but maybe I'm not...
But what will you see? How will you detect that this line terminates?
I think, from these poles, as I was saying, when one operator hits marginality,
Yeah.
I'm going in the other direction. Let's go to the simplest case. Then you have this pole here, and that means that you have a choice. Because when you integrate d delta, okay, with the coupling and this, you get a square root, and that means you have a choice of how to continue. So if there is a splitting, then by selecting one of the two branches of the square root, you will flow in one or the other theory.
There's no theory, it disappears at this point, so how?
Shadow symmetry? I don't understand, sorry.
Microphone.
Yeah, well, I also had another question, so...
Okay. So I'm not fully familiar. So I think the point is these lines, maybe they go back like this, and so here on the right, if you keep flowing with the coupling, you're asking what happens.
Well, maybe we can, with this question, maybe we continue. Another question is that one of the interesting consequences of the original Connor's paper was that he could give a rationale for the phenomenon of level repulsion. Do you see, this was an interesting consequence of his differential equations.
Do you see similar phenomena? Can you derive some effective models which explain level repulsion in this framework?
We haven't thought about it.
Okay.
Can I ask one last question?
Yes, let's do the last because otherwise we will struggle.
Okay, so the you said that as you go to larger and larger lambda, this is like approaching flat space limit. But then there's this expectation, right, that as you approach the flat space limit, all the scaling dimensions will grow proportional to its radius, so on. So can you analyze some sort of asymptotics of this form in your equations? See that that there is a scaling solution of this type?
But I guess that you don't expect all boundary operators to go, for example, linearly. I think that really depends on if the particular operator you're studying is related to some particle in flat space, right? And then that one will have a linear slope, and you can, from the slope, you can tell, or you can do the ratios of the masses. But I wouldn't think that that's something that you could say universally from the equations themselves.
I thought that's, roughly speaking, dimensional analysis, that you have energy spectrum flat space, you need to make scaling dimensions out of that, so multiply energies by R.
If the theory is gapped.
Yeah, the theory is gapped in flat
Okay.
space.
Yeah, I guess it would be interesting to think about it, but I don't know.
Okay, let's thank Manuel again. And okay, let's have a 2 minutes, so but we can make maybe a 4-minute break, and who wants to go, please run fast to the other end.